There we go. Let's start again. Okay, so welcome everybody. So this is the second Rose seminar that we'll be having today, and the idea of these seminars is to give an idea of some of the work and the research that is happening with the different students and researchers in Pavia in Italy. So the general idea is to have a presentation of roughly 40-45 minutes, and then we'll have some time for questions and discussion then afterwards. Okay. Just to avoid any problems with the presentation and interference, I would ask everybody to keep their cameras and microphones off so we don't have any disturbances or anything like that. And as I was saying before, that this I'm recording this video right now, so we'll be uploading the video to YouTube, and I'm putting the link to it on our LinkedIn page and stuff like that. So if you missed anything or want to see it again, it will be available online. So today's presenter is Gianrocco Mucedero, if I said that correctly. And so Gianrocco is a PhD student at IUSS Pavia, and the presentation is going to be on the topic of reinforced concrete frames with masonry infill. So the title of his presentation is the impact of masonry infill variability on the seismic assessment of existing RC buildings in Italy. So Gianrocco, the floor is yours.
Thank you, Gerard. So good afternoon to everyone, and thanks a lot for attending this presentation. I'm going to talk about the impact of masonry infill variability on the seismic assessment of existing RC buildings in Italy. So this is part of the research that I'm currently working on with Professor Riccardo Monteiro and Daniele Perrone. So I would like to start this presentation with pointing out the losses in Italy due to earthquake. So starting from 1968 to 2021, the losses in Italy are quite impressive. In particular, 5,000 people died, 500,000 people lost their own home, and for a cost of 1,150 billions. So conversely, the total investment in seismic prevention is in the order of 1 billion. So the idea is that in the last period, in the last few years, we in our consciousness related to the investment in seismic prevention is increased. So in fact, nowadays we have a guideline for seismic risk classification, which is based on two parameters, the ISB and the PAM. The first one related to structural deficiencies, the second one related to expected annual losses. And we have also Sisma bonus and super bonus, which are related to the tax deduction with respect to seismic strengthening intervention on existing buildings. And I can say that it is a unique opportunity to improve our the safety, the seismic safety of the existing Italian building. So if we take as an example the cost of L'Aquila earthquake, we have 10% of the losses related to structural elements and 90% to non-structural elements. So then if you look at the disaggregation of losses, 47% are related to infill wall and partition, 16% to plumbing and electrical system, 22 windows and doors, and the remaining portion is related to other elements. So in particular, when you see pumping and electrical system, but also windows and doors, the damage generally are also related to in plane and out of plane damage of infill and partition. So this means that masonry infill have a strong impact on the global and local behavior of structure, but also are important in terms of economic losses. So then when I started to work on this topic, I tried to ask me different questions related to two different, let's say, two different directions. So the engineering practice and the research. As you can see, the questions are quite different. And the next question was if there is a gap in between, or are different aims and objectives. So I think that the question, the answer is in between, and the research that we are doing in this period is going this direction. So trying to fill this gap and try to support the engineer in terms of indication on how to model the infill and which Masonry infill could they expect on a buildings, but also to quantify the impact of Masonry infill on the assessment of existing buildings. So we are going to see something related to material properties, modeling, and also a case study building portfolio. So starting from the material properties of Masonry infill, as you can see from this plot, there is a huge variability in terms of material properties. In particular, since there is no in situ material test characterization, the idea is to check the variability of the Masonry infill using database of collected experimental tests. And I just shown you some related to the work of De Risi and the one of De Luca. And from this plot, you can see that there is a huge variability in terms, for example, of modulus of elasticity, shear modulus, the vertical compression strength of the masonry, but also in terms of failure mode. So the idea is that for an engineer or for a researcher, it's quite difficult to guess the correct masonry properties of an infill to be used for the assessment of an existing buildings. So we decided to use this research methodology, and in particular to select 5 different Masonry infill typology, and based on this distinction is based on stiffness and strength. Then we used a macro modeling approaches for the infill frame, and we moved to a validation of the numerical model for the bare frame, and then we focused on the infill frame. In particular, there are different parameters to define the correct hysteretic behavior of the infill, and then we were able to define for each Masonry infill the correct models to be used to be representative of this specific Masonry infill. So, as I said, given a Masonry infill, there are different properties to be defined for the characterization of the hysteretic behavior, such as the strut width, in case of openings, how to reduce the stiffness and strength, the failure mechanism, and the backbone curve. So we start with the modeling approach of the infill frame. In particular, we decided to use a beam with hinges element and using both the flexural behavior and the shear behavior of the RC element, and they are aggregated in one section at the end of the element. In terms of beam column joints, we use this tube backbone curve, and the modeling approach was to use a zero-length spring coupled with a rotational hinge. This model was already validated by O'Reilly and Sullivan, but before to start the validation of the infill frame, we decided to further validate the numerical model. So starting from the gravity load design, this is the test proposed by tested by Verderame et al. In 2016. This is a gravity load design, so the frame is poorly detailed, and in particular, the assumption of rigid joints give us results that are overestimating the base shear of the frame, whereas the correct approach was to introduce a shear spring with the rotational behavior. And the results are in quite good agreement with the experimental test. Then we move to seismic load design frames. In this case, this is again a test of Verderame. On the right, there is a test of Morandi et al. In 2018. In particular, this since both of these are designed for seismic load, the detail of the joints are quite good, and the assumption of a rigid beam column joint give us results that are quite in good agreement with the experimental test. So then we move to the macro modeling approaches of the infill, and in particular there are different methodology starting from micro modeling or macro modeling approaches. We just focus on macro modeling approaches, and starting from the simplest one, which is the model proposed by Holmes, which is a single strut, to more complex one with 2 or 3 struts, which are able to catch the possible shear failure of the columns. There is also the possibility to use an hybrid solution, which is the one proposed by Crisafulli in 2000, which without any subdivision of the columns, the model is able to predict the increase of forces in the frame due to the interaction between the panels and the surrounding frame. One of the latest model proposed in literature is the one proposed by Furtado, which consists of two rigid struts in each direction, and they are connected to an element located at the center in which the nonlinear behavior is concentrated. To define the maximum strength of the panel, of course, it depends on the relative mechanism involved, and there are different possible failures, such as the shear sliding, corner crushing, diagonal compression, and diagonal tension or cracking. I'm not going into the detail of all of these failures, but I can say that are quite important when we go to define the models that should characterize the maximum forces in the panel. So these are just some of all the possibilities that are that we can find in literature, and I can say that among all of these, the only one of Bertoldi is able to consider all of these possible failure. Although it doesn't mean that is the correct one for all the Masonry infill typology, and this means that this is the first source of uncertainty in the model. Then we move to define the strut width. In particular, there are different methods. There are the methods based on the lambda parameter, which is a parameter which defines the relative panel to frame stiffness. There is the one proposed by Stafford Smith and another one by Pavia, or method based on a prefix value or a range of the ratio between the strut width and the strut length. And this is another source of uncertainty. Then often in existing building, we have also openings, which means that we are to take into account the openings. Generally, we reduce stiffness strength. There are also here different formulation, and the idea is to reduce the stiffness strength based on a percentage between the ratio of the area of the openings and the total area of the panel. And at the end, we are able to define the strength, the backbone curve to assign to the strut. And in particular, we used all of these to try to understand the reliability of the model. The one of Bertoldi, which is a quadrilinear backbone curve. The main parameter in this case is F max, which is based on the minimum of the 4 possible failures of the infill. There is the one of Panagiotakos and Fardis, also in this case is a quadrilinear backbone curve, and the main parameter is the cracking strength. Then in this test, this backbone curve is based on 10 experimental tests on infill frame with horizontally hollow crepe bricks. 2 novel approaches, which are the one of the Risi, which is a modification of the Panagiotakos and Fardis, both in terms of maximum forces. The residual is 0 in this case, and also in terms of stiffness. They changed the secant stiffness and also the softening to peak stiffness. The last one was the one proposed by Sassoon et al. In this case, the strength model is based on the approach of Bertoldi, but with the prefix value of drift capacity for each of the limit state. So at the end, we were able to define the impact of the numerical modeling approaches on the response of the infill frame. And in particular, given the test of Morandi in 2018 and the backbone curve, we are able to change all of these formulation, for example, the strut width and the strength model, and we got all of these backbone curves. So then if you use this backbone curve in a pushover analysis, you are going to get all of these pushover curves. As you can see, we got a lot of variability, so the variability is quite impressive. And also, if you look at the scatter between these pushover curves to the experimental one, the results are quite different. So in general, the idea was to use a statistical approach based on mean standard deviation to define the best model to predict the response of these experimental tests. So we got the model 1 and model 5 that are based on the backbone curve of Bertoldi, the strut width of Maidstone, and at the end, the strength model, both Bertoldi et al. And Poulain-Priestley give us results in very good agreement with the experimental test. In both cases, we use half of the initial strength of the bed joints, according to Gianrocco date. So if we now look at the disaggregation of the results, each of these subplot, we are changing the strength models, whereas in each of these, we are changing the strut formulation. So as you can see, the impact of the strut formulation is not so important, it's not so relevant, but what is important and the huge variability is coming from the strength model. So this variability is mainly due to the strength model. Then we use the same approach for the different type of Masonry infill that we select for the Macrolevel classification. And this is the case of the test of Calvi and Bolognini in 2001. This is an reinforced Masonry infill. And in this case, the best approach was for the strut from failure mechanism, the one of Bertoldi, whereas for the backbone curve, the approach of Sassoon. I wrote modified because we decided to modify the maximum axial deformation, the axial deformation of the struts at the peak response and collapse. So these are not the correct one for this specific Masonry infill. And in particular, it's quite interesting to say that these values are quite similar to the one proposed by Morandi et al. In 2011. They used the same experimental test to validate the same their own model. Then we try to also check the reliability of the model in case of openings. So the experimental test again is the one of Morandi in 2018, and the peculiarity of the test is the 8 of the openings. In particular, the 8 is equal to the 8 of the panel. This means that this Masonry infill is completely separated in two portions. And maybe for this specific case, the best approach is to use just one strut for each portion, as also demonstrated by the damage pattern at 1% of drift. Still, although this consideration, we decided to use the same numerical model that we use for the completely infill frame, but accounting for the reduction coefficient. And the best approach in this case was the one of De Canini that give us results in good agreement with the experimental test, although in this case, the scatter with the experimental test is more than before for the other validation model. So at the end, we propose a macro-level classification, which is based on stiffness and strength, and weak, medium, strong, and strong are related to the strength and stiffness of the panel. And in general, these are the best numerical model that we got for each of these specific Masonry infill. Moreover, the macro-level classification covered the entire range of variability that may be detected from in situ characterization test. These are just an example of the backbone curve for each of these Masonry infill according to the best numerical model that we got. And another idea is that from the outcomes, we noticed that the variability is not coming only from the material properties and the geometry, but also from the numerical model that we use to define the stereotypic behavior. So the idea is that we need to avoid any a priori selection of the model. Then, starting from this macro-level classification, we decide to quantify the impact of the infill variability on the assessment of existing buildings. So to accomplish this goal, we decide to develop a full integrated building stock, in particular accounting for the Masonry infill variability. These are all the Masonry infill, all the parameters that we use to define the the building stock. So according to the ISTAT database, 47% of buildings in Italy are masonry buildings, 29% are reinforced concrete buildings, and the remaining portion is characterized by other structural typology. 85% of the buildings are residential, whereas in terms of construction year, again, according to ISTAT, the massive portion of the Italian building stock were built around 70s, and there are no particular trend for different geographical area in Italy. In terms of plan geometry, we use urbanistic directives and population distribution, but also we check the results using satellite images and data provided in literature. For what concern the age of the building, again, according to ISTAT, half of the Italian building stock consists of two-story buildings, 24% of three-story buildings, 17% one-story, and the remaining portion, which are buildings with 4 or more story, is the 10%. This slide just to show you something related to the evolution of the Italian code with respect to the construction age. In particular, we focus on this specific construction age, the 70s, and at that time the seismic hazard was this. Another consideration is related to past earthquakes, in particular the one related to the Abruzzo in 2009. And according to Libro Bianco, which is a reference for the reconstruction process in L'Aquila, the buildings classify according to the EDES form as E, which means near collapse. This trend tried to decrease starting from 1946 to 2001, whereas the building classified by B and C increases, which means that the evolution of the Italian code is working quite well. So then for the definition of the material properties of the building stock, we use the reference of Verderame and those of Masi. In particular, for the steel, in that period of construction, there were different type of steel, and we use a mean value, in particular 350 MPa, whereas for the yielding strength. Whereas for the ratio between the ultimate strength and the yielding strength, we use a value of 1.4. For concrete, we use a value of 20 MPa according to this table. In particular, these are related to a work of Masi et al. In 2014. They collected a very huge database of concrete strength test in situ in Italy. Then we were able to define the entire building stock. These are all the main parameters that we used in the definition of the building stock. In particular, in the X direction, the length of the building is from 10 to 50 meters. In the other direction, the Y, the building length is from 8 to 25. The number of floors is from 1 to 6 floor. The span length is in the order of 3 to 5 meters. And the interstory 8 is 3 meters. If we select now one direction, we are able in this range from 8 to 25 to define discrete building lengths, in particular 7 according to the span length, and at the end we are able to define 18 different geometrical configurations. We define also 5 different configurations: the base frame, uniform free frame without and with openings, and the pilotis frame without and with openings. So we use also the 5 masonry infill that we select from the Macrolevel Classification, and at the end we were able to analyze the 2000 reinforced concrete frames. So this just to show you the workflow that we follow. In particular, after the definition of the material properties and the geometry, we design all of this frame according to the Italian building, to the enforced code in the 70s, using a simulated design approach. We select 2D frames, and then we perform pushover analysis. So now we can disaggregate all the results, in particular in terms of number of floors and in terms of structural configuration. And by doing this, we can, given a Masonry infill, to quantify building to building variability, or given an ID, which means given a geometrical configuration of the building, to quantify the infill to infill variability. On the other end, we can aggregate all the results, which means we are grouping the Masonry infill in weak, medium, and strong, and then we are able to perform a nonlinear static characterization of the entire building portfolio using a multilinearization of the pushover curves. So the modeling approach is practically the same of the validation. Then for what concerns the dynamic properties of the building stock. So in terms of structural configuration, for the base frame, the range of variation of the first elastic period of the building is ranging from 0.4 to 2 seconds, in particular for building of 1 story to 6-story buildings. Whereas considering the presence of the infills, the range of period is quite reduced. In particular, the blue one is related to the strongest Masonry infill, whereas the green one is related to the weakest one. And as you can see, the period is quite reduced. Whereas if you consider now the presence of the openings, the period increase again in the order of 35 to 50%. If you now look at the pilotis frame with and without openings, you can notice this peculiar trend. This is due to the fact that according to the past code, increasing the number of floor, we need to respect a limit, which is the maximum stress in the columns. That should be less than 6.5 MPa. This means that after these 3-story buildings, we need to increase a lot the columns at the base. And since we have no infill at the first floor, the behavior of the structure is completely governed by a soft story mechanism. Moreover, for this specific case, the impact of the openings is quite irrelevant, we can say, with respect to the previous one. Then we also checked all the results using for the infill frame without openings using simplified equations proposed in literature. The first thing to notice is the huge variability used one on another formulation. Secondly, the best formulation was the one of Gallipoli et al. In 2009, which is quite close to the median value of the entire building portfolio. And also the equation of Goel and Chopra, Olivero and Navarro, and Ricci are in very good agreement with the results, in particular in between the median of the case study building stock and the 60th percentile. In terms of pushover analysis, so this slide I'm presenting on the left the analysis for the infill frame without openings, in this case with openings. And in each of these subplot, you can see one pushover curve for each Masonry infill and also the bare frame structural configuration. These are the normalized mean capacity curves, in particular normalized because we are talking about seismic coefficient, so the base shear normalized with the total mass of the building, and mean curve because these are coming from all the analysis for the building stock for the same infill. In particular, you can notice the huge variability using one on another type of infill, going from the infill type 5 to infill type 1, which means from the strongest one to the weakest one. This variation is in the order, this variability is in the order of 60%. Whereas going from 1-story buildings to 4 or more story, the variation is the order of 80%. You can notice also that the seismic coefficient is quite reduced when we took into account the presence of the openings, which means consider the reduction of the strength of the panel. And moreover, also in this case, the variability given one floor is quite important. In this case, the variability is in the order of 75%, whereas going from one-story building to 4 or more story buildings, the seismic coefficient decrease in the order of 85 to 90%. For what concerns the pilotis frame, on the left, the case without openings, on the right, the case with openings. In particular, when we have frame without pilotis frame without openings, the impact of Masonry infill variability is practically zero. This because the behavior is practically controlled by a soft story mechanism, and going from 2-story to more story, 4 or 5 and 6-story buildings, the seismic coefficient decreases in the order of 52%. Whereas in this case, you can see that using an infill type 1 or 2, which are weak and weak to medium Masonry infill, we can notice some variability in the seismic coefficient, and the variability is in the order of 30 to 50%, 60%. Then we decided to quantify the building-to-building variability. So I'm just presenting an example for the base frame structural configuration and the infill frame with infill type 1. In particular, the variability around the mean is in the order of 13 to 16% until 3-story buildings. Then this variability is in the order of 30% for 4 or more story buildings, and this is also due to the fact that we aggregate in the 4, 5, and 6 story in only one plot. So for what concerns the infill to infill variability, the building to building variability, when we consider an infill type 1, this variability is in the order of 5%, so quite reduced with respect to the previous case, until 3-story buildings. And then this variability is in the order of 17%. So the idea was that the huge variability is not coming from the building to building variability, but from the intra-building variability, which means infill to infill. So this is just an illustrative example of 3-story buildings in which we are changing the geometrical configuration. So as you can see, going from one geometrical configuration to another, the seismic coefficient given a Masonry infill is practically similar. So which means that the huge variability is coming from the intra-building variability. Then we decide to plot also the mean and the standard deviation. You can see that if we now plot all of these mean and standard deviation inside one plot, the huge variability is due to the intra-building variability, whereas the variability due to building variability, is quite irrelevant. Also for the 4-story buildings and for all the other in the building stock. This is just another example to show you the importance of the number of floors in existing buildings. So going from 2-story building to 4-story buildings, you can see how much is reduced the seismic coefficient. At the end, we decide to do also another step, which is the simplified characterization for seismic assessment. So according to Van Vatzikos and Cornell, given a pushover curve, we can do a multilinear, we can fit the multilinear, we can fit a pushover curve with a multilinear backbone, in particular to get the SPO to IDA, using the SPO to IDA to get the IDA curves and also the collapse fragility. For the bilinearization, we use the approach of Dolcek and Pfeiffer, which is based on infill frame and is practically similar to the N2 method that we use in Eurocode or in the Italian code. And we noticed that the approach is it's worked quite well. Although in case of openings, we noticed some discrepancies. Then we use this approach in the entire building portfolio. So for the infill frame without openings and with openings, you can notice that each of these plots have now only three type of infill, because we aggregate in the weak one the infill type 1 and 2, in medium the infill type 3 and 4, and strong the infill type 5. Moreover, each of these curves represents the median of all the pushover curve that we performed, and the other one are related to the 60th and 84th percentiles. So the consideration in terms of variability are quite similar to those for the pushover that we already seen in the pushover curves. We have done the same thing also for the pilotis frame without openings and with openings. As we already see before, the variability when we consider a pilotis frame without openings, changing the type of infill is practically zero. Whereas when we consider a pilotis frame with openings, the variation of the seismic coefficient and the we can say the post peak branch is quite effective when we use a weak Masonry infill. So then we provide to the literature a table like this, in which the user can, according to a specific number of floor, can choose the Masonry infill and also all these points, which are the characteristic points of the multilinear idealized capacity curve. And the next step would be also to use this information to run the SPO to IDA tool. So in conclusion, the proposal of the macro level classification allows the engineer to use the material properties and the modeling approach for each of these that is consistent with the experimental test. And the idea is to cover the entire range of variability that they could expect in existing buildings. The variability is not only coming from the material properties and the geometry, but also from the numerical model that we select for the characterization of the theoretic behavior. The infill to infill variability is higher with respect to the building variability. Moreover, the idea is that we should avoid a priori selection of a numerical model for the Masonry infill, but should be select according to a specific characterization of the Masonry infill. Moreover, the impact of the Masonry infill is quite essential when we look at design of a retrofit or repairing intervention. Something related to the ongoing research. So we also quantify the impact of Masonry infill properties and modeling uncertainty on the seismic risk assessment of existing Italian school buildings. In particular, you can notice here the variability in terms of interstory drift and peak floor acceleration, changing the different, using different type of Masonry infill, and also in terms of expected annual losses, using both the uniform infill frame and the case in which we account for the presence of openings. Then we moved also we decided to quantify the impact of Masonry infill variability on the flow response spectra in RC buildings. In particular, you can notice the variability using one on another and the variability due also to building variability. But the most important thing is the variability and we can say the difference between the infill frame and the base frame. And at the end, we also performed a nonlinear time history analysis of the entire building stock that we see today. And we also performed a loss assessment with the idea to quantify the impact of the Masonry infill in the loss assessment of an existing buildings. So thank you very much, and feel free to ask questions.
Okay, so thank you very much, Gianrocco. Very nice presentation and a lot of information, I think. Okay, so do we have any questions or comments for Gianrocco on his presentation? I can see a lot of people clapping. Okay, so maybe I will just start with one question that I had. It was more of a curiosity related to the consideration of the openings you had on the infill. So one of the things you were mentioning in the last couple of slides was that the impact of the openings was something to consider. Could you just again explain how you were doing that and the relative impact it had on the backbone modeling, for example? I've seen some people do this in the past, but just to know
in terms of modeling.
Yeah. So the general consideration that you made, because there have been different ideas of how to do that.
So in general, the idea is that you can use different equation to do that, and there are different opinion. If the idea is we can reduce the stiffness, we can reduce the strength, or we can reduce both stiffness and strength. So in general, in literature, there are different equations to do that, and you just reduce the strut width of the infill to take into account of these aspects. So the reduction coefficient is based just on a ratio between the area of the infill, the area of the openings, and the area of the panel. Of course, this is a simplification of the reality for sure.
Sure. So it's in relation to the area of the openings. It's not it's a simplification like that.
Yeah.
Okay.
And also, it's important to say that this problem is also related to the location of the openings, the height of the openings. If the frame is completely separated into portions, as the case of, for example, the test of Morandi, like this, and so on.
Sure. Okay. Thanks. So, do you have anybody else?
I have just a quick question about the openings that Jared was discussing about. Which one of the expressions was most compliant with the experiments that you compared with?
So thanks, Karim, for your question. The best formulation was the one of the Canini et al. Although I can say that all the equations that you can see here are quite in good agreement with the experimental test that we used. So I think that the best one for our test was the one of the Canini, but also the one of the Davensier is quite good. So
okay, thank you.
You're welcome.
Thanks, Karim. Anybody else have any question or comments? No, I don't hear anything. I had one other question. It was about the modeling that you were doing. Yes, I see Volkan has a question, but I guess I'll finish now. About the modeling you were doing, yes, it was around here where you said, I think it was for the maybe 2 slides more, where you're comparing with the experimental testing of some, yes, here we go. So in the top figure, the top comparison you were making with the gravity load design frame, what was the difference in the modeling between the graph on the left and on the right?
So
the shear hinge, right?
Yeah, maybe. So the difference is that in this specific case, we used a rigid link to model the beam conjoint. So the joint is completely rigid, rigid behavior. Whereas in this case, the idea was to use a backbone curve. So the one that you can see here. And since the joint is poorly detailed, the assumption of a backbone calibrate on experimental test is better than a rigid beam column joint. Whereas in this specific case, the assumption of rigid joint, since it's designed for seismic load, is in good agreement with the experimental test.
Okay. I wasn't sure if, when you mentioned shear hinge, if you were mentioning the shear hinge of the actual joint or the shear flexibility of the frame membrane. But okay, yeah, that makes perfect sense. We had a question from Volkan.
Yeah, hello. An extensive work. Congratulations, Gianrocco.
Thanks, Volkan.
I just want to ask something came to my mind recently. You know, when you showed the losses, I was just checking. Have you tried to classify the results in terms of risk classification, such as the ones presented in Seismic bonus? I'm really curious if this kind of variability puts the structure from one risk class to the other one or not.
Yeah,
that's something I'm curious.
Yeah, thanks Volkan for your question. So this is something that we are going to do in this period. So to focus more the attention on loss assessment due to Masonry infill. So we also check these results with PACT. We use both PACT and also story loss function to do loss assessment. But as I can say that with respect to Sigma bonus, for sure you are going to get in general losses that are less than Sigma bonus. So for example, if you get 1% of expected annual losses in a numerical model, for sure with the approach of for example Sigma bonus, you are going to get 2%, 3%. So for this reason, there are different I can say results from Sigma bonus and the calculation that we can do with the loss assessment in research. In terms of difference between one infill typology to another, for sure there is a strong variation, as you can see from here. But at the moment, you can say, for example, type 1, type 2, type 4, type 5, you can have an increase of the losses due to the strength of the infill, and this is due to the acceleration sensitive components. So you are seeing that here you have an increase of the peak floor due to the strongest Masonry infill. But at the moment we have not checked these results with the Sigma bonus one.
Okay, because I guess most of the values are lower than 0.5%, for example, and if I'm not mistaken, it puts, for example, into the risk class of A. So in terms of risk classification, here I see that there's no big difference, but of course it depends on how you estimate the AL, of course. Also.
You do have, Gianrocco. You did
or not.
Remember that you have already carried out this for this school building. Okay, so you're not showing those results here, but you have done it. Of course, what Volkan is asking, so the jump from one class to another will depend a lot on the overall level of risk of the building. Because then it's when you are going to feel the impact more as well of the infills, because it also has to do a lot with the specific structural configuration, how the reinforced concrete frame part interacts with the infill, which one is damaging which. So for this specific building, if I remember well, Gianrocco, I think there was a change in the risk class for type 5, whereas type 1 to 4, they all belong to the same, right? If I'm not mistaken. But I just wanted to add that you have already carried out this, but just for specific, maybe a couple of school buildings at the moment, right?
Yeah, but the idea is that we need to check the results for the entire building stock. So at the moment we have done loss assessment using a story loss function, but we are going also to check the results using the Sigma bonus to understand the impact using the Sigma bonus on the results.
I see. Thank you. Congratulations again.
You are welcome.
Okay, we have any other? Yes, I see Riccardo Milanese is raising his hand. Go ahead, Riccardo.
Okay. Hi, everybody. Hi, Gianrocco. Nice presentation. I like it. I have just some curiosity, more than a question, I would say. Based on your, let's say, preliminary generic study of the kind of historical, let's say, building present in Italy and masonry infill and whatever, what kind of typologies and couples you find and you are kind of expecting to be more linked together? And if there is maybe some information that you find somehow missing in literature that may be useful for you or for the ongoing part of the study.
Thanks for your question. What do you mean with linked? When you say linked?
You connected somehow, something that maybe there are information missing that you may needed, let's say, or linked. I'd say maybe there are specific typology of infill more related to some specific ages and also typology of structure, of course.
Thanks a lot for your question. So the idea is that generally, if you need to analyze an existing buildings, you are not going to do any test of masonry infill. So this means that if you need to characterize the hysterectic behavior of an infill to take into account it in the modeling for the assessment, you are not going, it's like a blind prediction. So you are not going to have any information. And for example, if you look at the circolare, you have a range of variability of the masonry infill, but is not connected to a specific masonry infill. So you have no idea of the masonry infill that are connected this value, are linked this value to the specific masonry infill. So in general, I think that for new buildings, for sure, the company should provide to the engineer more information. For example, for infill, you are not going to have information on the vertical compression strength, the modulus of elasticity, and so on. For existing buildings, is quite difficult to do that. And I think that it's better to have a range of variability, as in this case with the Macrolevel classification, and to change this and to connect, for example, the shear strength of the masonry with a specific masonry infill, which means, for example, infill type 1 is the one tested by Calvi in 2001. So if an existing building, you have the geometry of the masonry is quite similar to that one, maybe you can use these properties and these modeling approaches. The same, for example, with the test of Morandi and so on.
Okay. Anybody else have any question or comment for Gianrocco? Don't see anything or hear anything. So I guess if there's no more question or comment, I guess we can just say thanks again to Gianrocco for his very nice presentation.
Thank you very much.
So as I was saying, we will upload this video as well that I've been recording, just so that if there's anything you want to see again, it will be available online. And lastly, thanks to everybody for joining. Okay, so we should have another one of these seminars in a few weeks. I'll send out the announcement in a while. It should be Martina Caruso, who, if I'm not mistaken, is listening in. So we'll keep you posted about that. Okay. So thanks to everybody, and have a nice evening.
Thanks.